Greetings all. Thank you very much for giving me this opportunity to introduce the core concepts of our webinar series. First of all, I'd like to provide an overview of microgrid, which is an emerging research area related to power systems. Let's have an idea about the conventional power systems. As we all know, conventional systems are based on large centralized power generating stations. In these power stations, mostly the electricity is generated by burning fossil fuel and producing steam, which is then used to drive a steam turbine. And that in turn drives an electrical generator, and the generated energy is delivered to the end user through complex transmission and distribution systems, as shown in this figure. This process appears seamless to the end user. For example, when you flip a switch, the electrical equipment turns on. However, there are some problems associated with the conventional power systems as they are based on centralized generating stations. As examples, bulk generation, heavy cascading failures, and heavy reliance on fossil fuels can be highlighted. The existing power network is subjected to the risk of cascading failures. What is a cascading failure? It is a failure in a system of interconnected parts in which the failure of a part can trigger the failures of successive parts. This may result in power interruption. For example, in industry, there is no or less production with grid power interruptions that results in a loss of revenue. And the next thing is the heavy reliance on fossil fuels. That causes emission of carbon dioxide, which results in life-threatening conditions and as a result of enhancing greenhouse effect. As we all know, greenhouse gas molecules trap heat waves that reflect from the Earth's surface and re-radiate towards the Earth. This disturbs the natural heat removal from Earth's atmosphere and results in an overall temperature rise. So in finding solutions for this greenhouse effect, the world is now more concerned in reducing fossil fuel and promoting renewable generation. And these are the key drivers to change the existing energy infrastructure. With the concern on changing the existing energy infrastructure, distributed generation concept has become an emerging idea. What is distributed generation? It is related to various generating technologies that generate electricity at or near the utility. This is also referred as cogeneration or small power production. Even home-installed solar panels, emergency generators, biomass-based electricity generation, and those things can be considered as distributed generation units. Let me mention some of the advantages of distributed generation. Most importantly, distributed generation saves the energy cost by reducing the contribution of centralized power plants. And also, this reduces transmission and distribution losses by producing energy at or near the point of consumption, which is a characteristic of distributed generation. And in addition to that, distributed generation encourages the unconventional renewable energy sources such as wind, solar, photovoltaic, mini hydro, and biomass. In addition to that, even in a failure of the utility grid, the properly integrated distributed generating units can maintain an uninterrupted power supply to the consumers within a defined electrical boundary. However, as we all know, renewable sources introduce power fluctuations such as weather dependability and resilient issues to the power systems. These energy resources require continuous control and monitoring to mitigate these issues. Therefore, the direct integration of renewable-based distributed energy resources will make the existing power network much more complex. Therefore, considering the mentioned inherent issues introduced by direct integration of renewable energy resources to the grid, the microgrid has come into the picture as a proper integrating platform. What is a microgrid? It is an electrical system, or let's say a small scale electrical system that is designed to provide power for a small community. A microgrid has a similar structure to our conventional grid, but most importantly, it can operate it in parallel to the main grid or as an electrical island. This is the basic structure of a microgrid. A microgrid comprises distributed energy resources, as you can see in this figure, such as solar photovoltaic, wind turbines, fuel cells, distributed loads, and power electronic interfaces, and point of common coupling. Microgrids operate, as I mentioned before, microgrids operate in either grid connected or islanded mode. When the utility grid fails, the point of common coupling allows the microgrid to disconnect from the grid and operate as an independent electrical island. And we know when it comes to conventional grid, large rotating machines introduce inertia to the system such that it will provide an excess time for the system to get stabilized in a cause of disturbance. Since microgrids comprise renewable sources that lack inertia, an energy storage unit has become a necessity. A battery backup or any other energy storage unit in a microgrid functions as a synchronous generator. In addition to that, microgrids often have technologies such as solar photovoltaic or microturbines, both of which require power electronic interfaces such as DC to AC converters or DC to DC converters, likewise to get connected to the electrical system. So this is the basic structure of a microgrid. Let's discuss the characteristics of microgrid. Local. A microgrid is generally focusing on catering nearby customers. Therefore, the produced energy is referred to as local energy because it is catering the customers nearby. This characteristic distinguishes a microgrid from the utility that involves long-distance transmission and distribution. Now, as we all know, long-distance transmission and distribution results in losses of generated electrical energy, but that will not happen in a microgrid. That means it is relatively lower, the losses are lower because of the nearby or the local generation. Microgrids have overcome this issue by generating at or near the point of consumption. The next characteristic is being independent. We know the grid connected solar PV systems that are installed and owned by consumers for domestic and commercial purposes are some sort of restricted to generate electricity when the utility grid is unavailable. So this is for the safety of the grid workers. And unlike a residential solar PV system, a microgrid maintains an uninterrupted power supply to the local loads by operating as an electrical island. That means even when the utility grid is failed, it can operate by itself as an electrical island. The next characteristic is being intelligent. That means that is one of the core concepts of our webinar series. We know most of the advanced microgrids are intelligent. So that means there are now intelligent control and energy management approaches for microgrid. We will be discussing those topics in our upcoming webinar series. Now let me give you an example. As you all know, an advanced controller in a microgrid can track real-time grid prices, for an example. And if the energy prices are inexpensive at any point, it may choose to buy power from the grid to serve its customers. rather than using energy from, say, its own solar panels. The microgrid solar panels could instead charge its batteries in the microgrid, and later in the day, when the grid power becomes expensive, the microgrid may discharge its batteries rather than using grid power. Likewise, advancing the microgrid operations with intelligent controllers, as I mentioned before, and these things will be discussed in upcoming webinars in detail. Let's discuss the modes of operation. In the grid connected mode, the utility grid is in the active state. The static switch is closed, as you can see in this figure. The utility grid regulates the frequency and voltage of the microgrid, and that allows the distributed generating units to follow the main grid's frequency variations. In the grid-connected microgrids, the demand and supply mismatch is overcome by injecting the excess power available in the microgrid to the utility grid and consuming the grid power whenever the in-house generation, that means the local generation, is insufficient to cater the local loads. In the islanded mode, the utility grid does not supply power to the microgrid. The static switch is kept open as shown here. The microgrid frequency and the voltage does not follow the variations of main grid as in the grid connected mode. In a grid outage or as scheduled, a microgrid can be isolated from the grid's distribution system at the point of common coupling. According to the diagram, all the feeders except for feeder C are supplied by distributed energy resources of the microgrid. However, even in the islanded operation, with the limited generation capacity and the heavy reliance of intermittent energy resources, it is required to minimize the demand and supply deficit or the mismatch and maintain an uninterrupted power supply to the critical loads. Therefore, sometimes it may require to set up a priority order for catering loads to ensure the important loads, to ensure that the important loads will get an uninterrupted power supply. Feed C, as marked in this figure, is considered as a feeder with non-critical load, such that let's say during the islanded mode operation, it is not supplied by the micro sources because it is not a critical load. So the other loads or the feeder A and the loads connected to feeder A and B will be supplied with the uninterrupted power supply because they are considered as critical loads. However, there are certain differences between islanded and grid-connected operations in terms of control, demand supply balancing, prioritizing, and catering loads, etc. This will be discussing in upcoming webinar sessions. Microgrid, the next consideration is microgrid architectures. The microgrid architectures can be discussed as power and control architectures. Based on the type of power lines, nature of sources, and operation, there are different power architectures. And microgrid control architecture can be centralized or decentralized or distributed or hierarchical. So the upcoming sessions will explain the microgrid planning and control and how this conventional and novel microgrid architecture development and the implementation. So let's discuss the desirable features of microgrids. Microgrid is a solution for the current energy crisis. The efficiency of a microgrid is quite higher than a conventional grid. As we have discussed, a microgrid comprises micro sources that are quite closely located to the point of consumption. Therefore, the transmission losses are lower in comparison to a conventional grid. In addition to that, microgrids encourage the high penetration of renewable energy resources because it provides a suitable integrating platform for these loads and distributed generators. And the contribution of microgrids in reducing carbon dioxide emissions and avoiding the consequences of large-scale land use are some of the major environmental benefits. And as another main advantage, I can highlight that a microgrid and is able to operate in both grid available and failed scenarios. The seamless transition from grid connected to the island mode and vice versa ensure the uninterrupted power supply to the loads. And this is quite important in supplying critical loads even in a grid failure. As a novel approach, uh, as Professor Dhyanga mentioned before, the closely located island microgrids can be networked as microgrid clusters. Let me explain what is a network microgrid. It is made of microgrid clusters that are physically connected and functionally interoperable. And the networking of microgrids allows these islanded microgrids to share their extra generation resource capacities among themselves. However, there are several limitations related to microgrids. Uh, as you know, the renewable energy resources in microgrids lack inertia, mainly rotational kinetic energy, spinning reserve, and storage. Therefore, these three attributes should be artificially created for these renewable energy resources. The inertia can be artificially created by adding energy storage units because the energy storage units can absorb mismatches in demand and supply within the microgrid and help in stabilizing the microgrid after disturbance. And continuous control and monitoring of intermittent renewable energy resources is another challenge in implementing microgrids, mainly in islanded mode. Voltage, frequency, and power quality should be controlled such that these parameters comply with the standards imposed, and it is in addition to the common demand supply balancing. After the discussion of microgrids, let's have an idea about the smart grid concept. A smart grid is an electrical system integrated with communications and information technologies for enhanced grid operations, customer services, and environmental benefits. These are the characteristics of smart grid. The first one, self-healing. Self-healing refers to the ability to identify power grid problems in real time and safely respond by self-correcting. The next one is distributed. The distributed nature of a smart grid ensures the integration of the decentralized power generation such as solar panels, wind turbines, and biomass-based generators. And also, smart grids combine intelligence and control for, let's say, optimal utilization of power production as well as energy storage resources. Predictive. The predictive nature of smart grid, it is generally refers to the measurement and analysis of, let's say, anomalies that affect power quality to prevent emergencies from occurring. The key to achieving these previously discussed potential benefits or the functionalities of a smart grid is the successful build-up of smart grid communication network. And as you can see in this figure, there are two layers. That means in a smart grid, in parallel to the power infrastructure, there is an underlying communication network. We generally consider that as the backbone of a smart grid. As all of you can see, there are three communication network architecture layers that are based on wide area network, neighbor area network, and home area network. Let's discuss about these networks briefly. Home area network supports, let's say, homes, buildings, industrial automation based applications. They're mainly to send or receive sends data from these electrical appliances installed in these utilities. And these signals will be sent from the built-in controllers of these appliances. The main requirements of this network is less power consumption, less cost, and easiness and secure links for communication. The next one is neighbor area network. The neighbor area network supports smart metering and distribution, smart metering, and also distribution specific applications. These things will be discussed in our upcoming webinar sessions. And this is also aims on sending or receiving the transmitted data from these customers or its field devices. There are some requirements for that particular network, as it requires a high data rate, and also it focuses on a large geographical area in comparison to the home area network. The last one, the last section is the wide area network that supports a wide area control, protection, and monitoring. And the main requirement is to transmit a huge amount of data at a much higher data rate, and mainly over a longest distance in comparison to neighbor area network and home area network. These are the main functionalities of smart grid. First one, the advanced meter infrastructure. The advanced meter infrastructure generally allows utilities to collect, measure, and analyze energy consumption data from various purposes. For example, I can say grid management, outage notifications, or let's say for billing purposes. For these things, advanced metering infrastructure is quite important, and it is one of the main functionalities of a smart grid. The next one is demand response, and it is one of the most common steps taken by utilities in creating a smart power grid. And what is demand response? It is about reducing the electric energy consumed by customers in response to an electrical price increase, or some sort of a heavy burden on system, or let's say for the requirement of the system. And another functionality of the smart grid is better and more uniform integration of distributed energy resources and storage. And the next one is electric vehicles, the next concept, and it is one of the main concepts of smart grid functionalities. And when it comes to the electric vehicles, they contribute to the reduction of emissions and energy. It is because of their ability to provide sufficient electricity supply for such vehicles depend on effectively management of supply and demand. So that is why it is one of the main functionalities of a smart grid. And we can consider it as a core benefit of a smart grid. And when it comes to new research areas, as a novel approach, there is more consideration towards researching about electrical vehicles function as an energy storage device in balancing demands on the smart grid. That means absorbing excess supply during the periods of low demand and feeding that energy back into the grid when necessary. And the last point, the wide area situational awareness, and this refers, the definition is to the implementation of a set of technologies to improve the monitoring of the power system, and it is basically across a large geographic area, and that is one of the main important points regarding wide area situational awareness. And this provides the grid, let's say the grid operators with a broad view and a dynamic picture of what is the function of the grid at an instance. Let's see how the smart grid concept and the microgrid concept are related. As we discussed, smart grid is referred to the modernization of existing grid with advanced communication and information technologies. But the microgrid refers to a localized version of a power grid. That means it usually separate from the national grid for supplying power to remote or isolated areas. So when it comes to the relationship between microgrid and smart grid, a microgrid is a small scale smart grid. It can be considered as a subset of smart grid. Smart mean a small scale grid refers to a microgrid, while smart mean the utility grid, let's say the macro grid, refers to the smart grid. This means the concept of smart grid applies to any unit of power system that's made intelligent. A complete microgrid solution is an integration of microgrid planning, control, and protection. In our upcoming webinar series, we will discuss designing and developing a microgrid solution in detail together with microgrid modeling, mainly with MATLAB and other softwares as relevant. And the Smart Grid Research Lab of University of Moratuwa cordially invites you all to the next session of our webinar series. The next session will be based on distribution system automation, and it is presented by Mr. Dinesh Disanayaka, and it will be held on 9th November from 6 p.m. onwards. So thank you very much.